All right, let's continue our study here. We're going to move along with exponential decay. You can notice that the general form of the equation is the same. So our A value is still our initial amount. Our B value is our growth factor. But in this case, when we start looking closer, our growth factor is going to be less than 1, but greater than 0. So keep that in mind. So those two values, A and B, start out in the same way. It's different in its application, because what we start to see is that B value, we get decay when it's between 0 and 1. So we start getting like numbers like, obviously like 0.5. That's that, or 1/2. That's that idea of like, exponential decay, of course. Yeah, but half-life. Half-life is a very common kind of application to these problems. So from science, when we talk about in chemistry, we talk about the half-life, how long something takes to decay a certain element. That gives you that example of how exponential decay is applied to real life. So let's say we have a function that is considered decay. It has some similarities to growth, but obviously, as we look way out to the left, we're going to start with a greater amount. And as time goes by, or as the value of x increases, our graph decreases. And so it's going to, in this case, way out to the right, way out to the big numbers out there for our x value. Because it's a number less than 1, it's being raised to a larger number. It's getting smaller and smaller and smaller in its amount, closer and closer to 0. Never reaches 0. We'll look at that again as we go into Desmos. But the graph itself, it's really kind of a flip over, so to speak, of this exponential growth. So this y-intercept is still going to be 0a. So when you see that A value, you can bank on the fact that that is always going to intersect there on the y-axis. Our domain and our range is very similar. The domain is going to be all reals again. So we're going to go from negative infinity to positive infinity. And our range in this case, it's going to go from negative infinity, and it's going to get really close to 0, but it's actually never going to get to it. So how does that then show up with an asymptote? So you're going to see the asymptote. It's very similar. The asymptote is still going to be our y equal to 0. Horizontal, y equal to 0. In behavior, so we are going to say it this way: as x approaches negative infinity, our y value, or our f of x, is taking off to positive infinity. So as we look left, it's way up there. And then if we look right, so as x goes to positive infinity, y is going to take off. Well, it's not going to take off. It's going to narrow in. It's going to get closer and closer and closer to 0. So let's look at an example again. Instead of having our growth factor, we're going to start with our amount 3 here. So our A value is going to be 3. Our B value is going to be 0.5. So when we go look at this at Desmos, we will see indeed how this function is behaving to what we have in our picture above. So let's turn this one off. Let's go to our next one here. In this case, we're going to go to f of x is equal to, and we're going to go 3 again. And use parentheses for my multiplication. This time we're going to go 0.5 or 1/2, and we're going to raise that to the x. And we should see that indeed we get this decay situation. There is our y-intercept again at 0, 3. In behavior, as we're looking left, as we're looking this way, sorry, I wish I had my cursor. Here we go. As we look to the left, it's way up there. And then as we go to the right, as our X values increase, it's getting closer and closer and closer to 0. It'll never touch it, but it'll get closer and closer. So if we get way out here and we zoom way in again, you are going to see that indeed it's going to start raising up off the, looks like it's touching the x-axis, but it actually isn't. We get closer and closer. It's going to take a while here. But look, it's starting to come up. You can start to see it come up off the x-axis. All right, so put that back at home. How would we graph this, either one of these functions, if we had to do it without Desmos? Well, if you look in your text, it's the same way you've been graphing since you were first looking at graphs, like lines. So it's going to be done using a smart chart or an input-output table. So you're going to put values in for X and get values back for Y. Let's just mess with this for a second. Let's deal with some numbers. Grab a calculator here and you can check as I go. But let's start out in the negative. Let's say we're out here at -3. So if I raise, you can use the calculator. I'm going to show you the math, the actual math. If I take this function right here, we'll use this same one. If I take 3 times 0.5 to the x, I'm going to take 3 times 0.5 to the -3rd. Well, 0.5 to the -3rd is actually 1/2 that's being raised to the 3rd power. That's going to be 1/8. So we're going to go 1/8, which is 0.125, I believe, times 3. Oh, I'm sorry. Just the opposite. It flips it over. My bad. It's going to be actually 1/2 to the -3rd. That's going to flip the 1/2. It's going to take it to 2 to the 3rd. So 2 to the 3rd is going to be 8, and then you're going to have 8 times 3, which is what, 24. So double check that because I messed that up in my initial explanation there. But if I take 3 times 0.5 and I raise that to the -3rd, you're going to see that you get 24. So at -3, we get 24. All right, so let's just follow along here. I'm going to jump up to -1, let's say. So at -1, I skipped one there. If you want to put -2 in there, you're going to probably see that it's going to be half that. It'll be at 12. It should be at 12. And then at 1, it should be, I believe, at 6. You can check that. So at -1, we should have 6 because we're going to have 3 times. Let me move this up here. We're going to have 3 times 0.5, and this times to the -1. That's the same thing as 3 times 2, because 0.5 to the -1 is actually 2. And so we get that 6. Again, check that. If you don't trust me, I'll check it too. But we'll raise that to the -1. We get 6. And then now you can, so that means that it started up at 24. Think about that. It went up 24 at -3. So off to the left here, it's at -3, or excuse me, at -3, it's up at 24. At -1, it starts coming down. It's at 6. And then at 0, hey, here's an explanation as to why it's always going to be our y-intercept at 0a. Because anything to the 0 power, 0.5 in this case, 0.5 to the 0 power is 1. And so if we take 1 times 3, we're going to get 3, obviously so. And then as we increase, it's going to get smaller and smaller and smaller. If you take it to the first power, you got 0.5 times 3, that's at 1.5. You take 0.5 to the second power, that's the same thing as 1/4. So 1/4 times 3, that's 3/4, 0.75. We're getting closer and closer to 0. Check it out. Look at the examples in the book. I'll go over another example here with the next video. An application problem as well is coming. And then we'll close up shop here on this one. All right, see you in the next video.